Okay. Let us begin. So, last class was admittedly a bit of a whirlwind, but hopefully you got from it what you should have got from it, which means the things you should have memorized. So let's actually check before we move on. Define f prime of x. What's the definition? Go, just go.
The limit as h approaches 0 of f of x plus h minus f of x all over h.
State the chain rule. This is where you go. Anyone just keep calling it. Just go.
Prime g prime of x times g prime of x.
No.
No, wait.
Chain rule is an equation. State the chain. Yes?
The f of g of x, is that the equation, the f of g of x?
The
The
derivative.
derivative of f of g of x is equal to f prime times g of x
Of g of x.
Of
not
g of
times,
x.
not multiplication.
times the derivative of g of x.
Okay. State the product rule.
The derivative of f of x times g of x equals f prime times g plus g prime times f, or vice versa, whatever.
State the quotient rule.
The derivative of f divided by g is equal to g prime, no, I like, g times f prime, or
Right?
whatever.
Bottom times derivative of the top.
minus f times g prime
Top times derivative of the bottom.
divided by g squared.
Or the bottom squared. State the power rule.
The derivative of x to the n is equal to x to the n minus 1 times n prime,
Times what?
times the derivative of n.
No.
It's equal to n times x to the n minus 1,
What is n here?
a number.
Constant. Okay. What is the derivative of an exponential raised to a function?
Isn't it e to the u times u prime?
What is the derivative of ln of a function?
1 over
1 over u.
u times u prime.
What is the derivative of a logarithm to the base a?
1 over x log n. No, x ln n.
What else did I tell you guys about? Chain rule, product rule, quotient rule. And by the way, you should have this all in your head. You shouldn't have to look at your notes to be able to regurgitate this. That's going to be very important. What was the derivative of sine? X.
Cosine x.
Cosine. What is the derivative of cosine?
Negative sine x.
What is the derivative of a to the x?
A to the x times ln of a.
What is the derivative of a to the u?
The derivative of u, au ln a.
Should have that all in your head. Immediately accessible. Yes.
If you ask us to ever like write these down, right? We have to do it with it like as the equation form?
Yes.
Okay.
It is not okay to memorize one side of a rule.
Okay.
So you have to have the entire equation in your head,
Okay.
including the derivative part.
All right.
Okay, so if I had to differentiate, let's say, one function plus another one, how can I do that?
Derivatives distribute across sums.
Okay, so
So the derivative of f of x plus the derivative of g of x.
therefore, if I say multiplication here, what is that?
Product rule.
Derivatives do not distribute across product. I was going to see if someone said f of x times g of x. Okay, right, product rule, that's f prime g plus fg prime. By the way, just a pro tip here. Product rule can be extended in a pretty natural way. So you would have it memorized for two things, but it turns out that you can extend it to n things. So if, let's say you had three things. The product rule in general, in the single variable case, you can think of it as the following. It's just a sum of all the products where a different function gets to be the derivative each time. So if you have three things being multiplied and you want to apply the product rule, it's going to be f prime, leave the other two, g prime, leave the other two, h prime, leave the other two, right? And if there were four, you'd have a sum of four things where each function gets to be the derivative in one part of the sum. So if you have f, g, h, you get f prime ghi plus fg prime hi plus fgh prime I plus fgh I prime, etc. The product rule extends very naturally in that sense. And you can prove this just by applying the two variable one over and over. So to prove this, you can just think of g and h as one function, and whenever you're finding that prime, you expand with the product rule and multiply out, you'll eventually get a pattern like this one. That's just something that would be nice for you to know. Let's actually look at some more examples. Let's figure out how to differentiate the other trig functions. What if I wanted to find the derivative of tangent? Yes?
Did you do the quotient? We know like the derivative of sine and cosine, and we
Yeah.
know the quotient rule, so you can combine
Right,
those.
so we can realize that this is just sine divided by cosine. We know the derivative of each of those, and we can just apply the quotient rule. So this is equal to, by the quotient rule, what would it be equal to by the quotient rule? Yeah?
The cosine of x times sine of x minus sine of x.
No.
Oh wait, cosine x times cosine x.
All right, it's the bottom times
Yeah.
the derivative of the top minus.
Then minus sine of x times negative sine x all over cosine squared.
All over the bottom squared. Now this we can simplify. This will give us cosine squared. Here there's a minus and a minus that will turn that into a plus. So on the top we'd have cosine squared plus sine squared, which is
1.
it's just 1. So we get 1 over cosine squared, which as you might recall is secant of x. So that tells us that the derivative of the tangent function is secant squared of x. And of course, by chain rule, we know that the derivative of tan u is going to be u prime secant squared u. That is now another thing you should have memorized. What about something like secant? How would you figure that one out?
Secant is equal to 1 over cosine. Which is also the same as cosine to the -1. That makes it easier. Can you use the power rule in this case or no?
No,
It's chain,
it's chain rule.
so
Power rule works when the base is x.
so negative cosine x times negative sine x.
No. So the outer function is the -1 power. How do you deal with that?
The negative second.
Huh?
Subtract 1.
From?
Negative 1.
Okay, so what is it?
Two.
So we need -2 power here. Then we're going to multiply by the derivative of the inside. So that's going to be?
Which is negative sine x.
So this is the chain rule. Right? Of course, you could use the quotient rule. Just remember the derivative of 1 would be 0 if you're doing it that way. However, at this point, we have the following. The negative and negative sign kill each other. So we have 1 over cosine squared x times sine x, which some prefer to write this as 1 over cosine x times sine x over cosine x. Sine x over cosine, we know is the tangent function, and 1 over cosine, we know is the secant function. This gives us the fact that the derivative of the secant is secant x tangent x. And of course, we can do the chain rule version here. If it was secant of u, it's u prime secant of u tangent of u, etc. Right? Every time I give you a rule, there's always a chain rule version of it. I'm not going to prove the other ones. I'll just state them, but you should try to prove them on your own as a practice here. Also, the derivative of, who did I miss? Cosecant is going to be minus cosecant x cotangent x, and the derivative of cotangent is going to be minus cosecant squared x. So it's in a box, which means the next time I see you, should be able to regurgitate this without looking in your notebook. That's what putting things in a box means. So differentiate the other trig functions. So now we know how to differentiate polynomials, exponentials, logarithms, radicals, all the trig functions. Maybe, just to get us used to taking derivatives, maybe we'll do a few more examples. And then maybe I'll talk about the existence of the derivative. There are a lot of things I want to tell you, but I'm trying to decide which one do I want to tell you first. Probably talking about the existence would be nice. would flow better. Let's do some more examples. So, not learning anything new, just trying to apply what we already know. See if you can let's get through those. Probably a few more. I'm going to find out the derivatives of all those functions. Okay, go. What do we do?
Quotient rule.
Quotient rule? Okay. So that's going to be?
X cosine x minus sine x all over x squared.
Probably just do that. E. Quotient rule again. Okay, what it would be?
X plus 2 minus x plus 1 all over x plus 2 squared.
What does that simplify to? Does it simplify?
Yeah, simplifies to 1 over x plus 2 squared.
Or do this one? Yeah.
Just power rule.
Okay.
Derivative of x squared is 2x divided by 2.
Okay. So, very simple case where I just wanted to bring up a point. You see a division, doesn't mean you should just blindly apply the quotient rule. The quotient rule and product rule, there are cases where you can apply them, but sometimes it's just not worth applying them because it actually makes your life a lot harder. So quotient rule would be overkill here. Just realize that x squared over 2 is the same as 1/2 x squared, so you can essentially apply the constant factor rule. So if there is a constant in the denominator, you can essentially just leave it alone and differentiate the numerator. So don't take the time to go through the quotient rule. Often what will even happen in that case, especially when students are anxious, they'll forget that the derivative of 2 should be 0, and so they'll actually get the wrong answer when they try to apply the quotient rule. So you only need power rule here. So if the denominator constant, just leave it alone, differentiate the top. Very simple idea, but it could look much more complicated than this. Let's talk about D. How do you do this one?
You can think about it as 3 times x to the negative 1/2, and then just do power rule.
Ditto. No quotient rule. If top is a constant, rewrite using exponents, chain rule to take effect. I mean, here we could apply the power rule, but it's equivalent, it's equally the same as applying the chain rule. And we actually did this already when we derived the derivative of secant. We thought of it as 1 over cosine, but we didn't go through the quotient rule. We just brought the cosine up and did the chain rule. So some of these rules I'm giving you, they're very powerful, they're very important, but sometimes like using a bazooka to kill a mosquito, you don't need to apply them just because you see a division or a multiplication. So I just threw some silly examples in there to illustrate that point. Sometimes you don't need to go to the product rule or the quotient rule. What about E?
This one you have to use the product rule and the chain rule.
Right, because I'm not going to expand something to the 8th power or the 5th power to use the power rule, even though in theory that could work. That we don't, ain't nobody got time for that. Okay, so how would that be applied here?
So it would be 8 times the quantity 2x plus 1 to the 7th times 2.
Right, that's the chain rule multiplied by the derivative of the inside function here after differentiating the outer function, which is the 8th power. Yeah.
Times the quantity of x squared plus 1 to the 5th
Times this,
plus.
just for a little bit of emphasis here, that's with thinking of this as your f and this as the g. This is f prime times g here. Plus,
So then I have to do g prime times
right,
f.
now we're going to do our f times g prime.
So f is just 2x plus 1 to the 8th. And then g would be 5 times the quantity x squared plus 1 to the 4th times 2x.
So we needed the chain rule to differentiate each of those, but you should just realize that you're just differentiating one at a time and creating a sum. Simplify this.
times.
Sure, 8 times 2 is 16.
Yeah. You can also pull out, you have 2x plus 1 in both, so you can pull that out. You can pull it out to the 7, and then,
Right? 2x plus 1 is a common term. In one term, it's raised to the 7th, and the other is raised to the 8th. You always pull out the lowest power, so you pull out to the 7th.
and then you can pull out x squared
X squared plus
4.
1 is also a common term. The powers are the 5th and the 4th. You always pull out the lowest power. 2 is also a common term. So I can pull that out. Okay, what do we have left here? So what would I have left here? Yeah?
8 times x squared plus 1 plus x minus 2x plus
5x.
yeah.
That's that. Let's just simplify in here. This will give us 8x squared plus 8. This guy would give us 10x squared plus 5x. And so we would have 2 times 2x plus 1 to the 7th, x squared plus 1 to the 4th, times 18x squared plus 5x plus 8. So that would be that derivative. So this is the derivative, this is a simplifying, but as you will see, there will be times where we want to figure out when the derivative is 0, and in order to do that, if setting that equal to 0, how you would go about solving that would be to factor, and then set each factor to 0. So you do have to remember, of course, your algebra. No surprise there. We'll talk about those applications pretty soon for the derivative. Right now we're just practicing finding them and simplifying them. What would f look like?
Just a question, for something like this, would you care if we made the 5 a negative exponent and use the product rule instead of using the quotient rule?
I wouldn't care.
Okay.
I don't particularly think there's an advantage to that though, but psychologically, or by preference, students might prefer it one way or the other. I don't particularly think there's an advantage to it, but if that's how you do it, there's nothing wrong with that.
Okay.
Because in the event that you need to simplify like this, if you do it that way, the product rule is going to give you 2 terms, which to combine them, you're going to have to find a common denominator. And so that extra step in the event that you have to simplify something kind of trumps whatever speed you gained by thinking of it as the product rule versus the quotient rule.
Okay.
But it's not wrong if you do it that way. Just be aware that in the event that you actually need to set the derivative equal to 0, you're not actually saving time. It's just a matter of preference at that point. So yeah, here we can do the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. What's x squared plus 1 to the 5th squared?
X to the 4th plus 2x squared plus 1.
No, the denominator is this to the 5th.
Oh, I'm sorry.
Yeah, what's the
I think
square?
I didn't. What was your question?
What is the square of the denominator?
Oh, so it's x squared plus 1 to the 5th times x squared plus 1 to the 5th, which is x squared plus 1 to the 10th.
I just want to make sure you know to double the power, not square the power. Okay. So, right. Raise something to a power to another power, you multiply the power, so that becomes the 10th power. And now, to simplify this, you do something similar, you start factoring. So again, 2 is a common term, 2x plus 1 is a common term, raised to the 7th. X squared plus 1 is a common term, raised to the 4th. We would be left over with 8x squared plus 1 minus, instead of plus, it's going to be like this, but it's going to be minus 5x 2x plus 1 x squared plus 1 to the 10th. We'd be able to turn that into a 6. So we have 2 times 2x plus 1 to the 7th times, this would be 8x squared minus 10x squared minus 2x squared. And that would be minus 5x plus 8 all over x squared plus 1 to the 6th. How would you differentiate that?
It's u prime, it's, well, we found the derivative in the last one, times u, which is 2x plus 1 to the 8th over x squared plus 1 to the 10th.
Well, it would be u prime divided by u,
Yeah, sorry, that's what I have.
right? Pretend you didn't know that. How would you have done it? There's an easier way than going through that. That's what I want you to see. Do you see another way than just brute forcing the quotient rule and putting that all over that?
You flip them, and then find u prime,
How would you flip it?
like x squared plus 1 to the 5th over 2x plus 1 to the 8th, and then find, it could be wrong,
Well, that's the same thing,
it is.
right? If you divide by that, it's the same as multiplying by its reciprocal.
Can you chain rule?
How? How?
No, it's the same as the other thing.
Just be the same thing. U prime over U. There's an easier one. Hint, there's an ln here. No, doesn't help. Do you have an idea?
I mean, there's an ln, so you could rewrite it as e, but I don't think that helps us.
Well, we can't rewrite that as e. Well, we can, but it wouldn't really help, would it? Well, that's very important. When do you know you can rewrite something as e when there's an ln?
We would need the other side.
You need an equation, so you wouldn't
Yeah.
really do that anyway.
We would just have another.
Right. If this was equal to something else, then yeah, we could raise both sides to the e and rewrite that. We have log of a division here.
Oh, can you change it to subtraction?
You can change to a subtraction of logarithms. And you immediately see that's easier, right? Now I don't need the quotient rule. We could make it even easier. Yeah?
Powers.
The powers I can bring down. Notice I'm not taking derivatives yet. I'm simply using the algebraic properties of the logarithm to simplify it a little bit first. So what I have now is 8 ln of 2x plus 1 minus 5 ln of x squared plus 1. Now we can take derivatives of that with minimal difficulty. Okay. That's 8 times the derivative of this over that minus 5 times the derivative of this over that. If you want to rewrite this as 16 over 2x plus 1 minus 10x over x squared plus 1. And if the mood happens to strike, you could simplify that. And it turns out that that guy will be equivalent to taking this guy divided by this guy, which is left to the rigor to verify by 10. But yes, don't forget your log and exponential rules. There are times when it can be beneficial to simplify before taking a derivative. We are going to cover something called logarithmic differentiation, where we can introduce a logarithm to take advantage of its properties, as opposed to brute forcing something that would be a very annoying quotient rule, for example. So yes, we are in derivatives now, but do not think that gives you license to forget all the things we've done up to this point. Everything we've done so far is relevant. It will always be relevant. And any point in time, you might have to recall, oh, something we did way back in lecture 2 is going to help me over here with derivatives. What about h?
Oh, isn't the square root of e plus 1 just a constant?
It is just a constant.
So it's, you can move that out and take the derivative, which is x to the third, which is 3x to 3x squared.
Okay. That's derivative. Just want to make sure of that. that is a constant. You should recognize that that's a constant. We'll probably do some more examples next time. We'll also introduce next class I'll probably do implicit differentiation as well as higher derivatives. But for now, let's talk about existence. So we learn these rules and you realize that even with very complicated functions, we have the power to find the slope to that curve at a particular point. You might be like, we've solved the rate problem, we are all powerful. It turns out things aren't that peachy. There are times when we cannot find a derivative where the derivative would not exist or not make sense. And so we should be aware of situations like that. So let's start off with an illustrative example here. Suppose we want to find the derivative of the absolute value of x at x equals 0. Okay. So this was our goal. Right? We're looking at the absolute value of x, very innocent function, a function we're used to, nothing terribly complicated. But we want to find the tangent line to this function at the origin. Right? We know the function is continuous there, the function exists there, the function exists for all real numbers. So we want to do that. Now, I'm going to do this by the definition, just so you can see what happens here. So we know that the derivative, and I can show you another way. Using the fact that f prime evaluated at some point, you can think of that as the limit as a approaches 0 of f of a plus h minus f of a all over h. Right? We can just plug in the point and evaluate that limit. Now, this means if f of x equals the absolute value of x, then if we find f prime of 0, well, that'll give us the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. What is f of 0 plus h in this case? For f is absolute value of x. Yeah? Coming in?
I don't know.
F of x is the absolute value of x. What is the absolute value of 0 plus h?
H.
No. How do you find composite functions? What does it mean to say f of 0 plus h? Well, it means you go to the function and everywhere you see an x, you replace it with 0 plus h. So we have absolute values of 0 plus h minus f of 0, the absolute value of 0, all over h. Simplifying this, we would end up with the absolute value of h divided by h. And what is that?
Undefined.
This limit does not exist. For a very innocent looking function, it's actually impossible to find a tangent line at this point. Now you might say, what's going on at that point? Why is it not working out here? Well, you'd realize that the absolute value function looks like a V. Okay. So over here we have y equals x, and over here we have y equals minus x. Which means that if we were to take the derivative one side at a time, the derivative on this side, your y prime, would be equal to 1. And the derivative on this side would be equal to minus 1. So it turns out that if you're at 0 on either side, your derivative function is not agreeing. Right? So that limit is not going to exist. You could have also looked at it that way. Understanding that you are finding the derivative evaluated at 0, you'd realize that this is just, well, it's the derivative of x, if your x is greater than or equal to 0. It's the derivative of minus x, if your x is less than or equal to 0. Which means you can either have 1 or minus 1, depending on the direction you're coming from. And that would mean that a limit would not exist. So this illustrates one situation in which a derivative cannot be found. And the idea is, remember how we developed the derivative? We pretty much wanted to approximate a curve using a tangent line. So the idea is, we can differentiate at a point. If we zoom in on that point, it will start to look like a straight line eventually, right? Things will start flattening out. But it turns out, if you have a sharp corner, no matter how much you zoom in, it's a sharp corner. It's never going to look flat, right? A point is never going to flatten out no matter how much you zoom in, right? So this kind of talks about when a derivative may or may not exist. Basically, the derivative will exist if, as you zoom in on some region, it starts to flatten out at that region and look like a line that we can write down as y equals mx plus b. And so in all other cases, it turns out your derivative would not exist. So this illustrates one way in which the derivative would not exist. There are others. Which is where we'll end things today. F prime cannot exist in, let's say, 3 situations. So the first situation is illustrated here at sharp corners. Anytime we have a function that has a sharp corner, derivative will not exist. A sharp corner, you might see the word cusp being used to. At any point, f is not continuous. If your function doesn't exist there, if there's a gap or a jump or a hole, you can't draw a tangent line there. The point doesn't even exist to be able to draw a tangent line to. So we need continuity. So if there's a sharp corner, can't find a derivative. If it's not continuous, can't find a derivative. Third situation is there are some functions that can have vertical tangent lines at certain points. and the derivative will not exist at that line. So you can have a function that does something like this. And at one point for a split second, the best line to approximate it would be a vertical line. We know that vertical lines have no slopes, and the derivative is literally the slope. So we'll pick up next time, or we'll stop there. And I'll see you guys on Friday. We have a quiz today.
Is it focused on
stuff
like the rules?
Yes, the rules and